Welcome to Video Lessons by Cloud Deck. Consider this explainer your highly technical, deep dive masterclass tailored specifically for you DGCA CPL candidates out there. We're going to completely unpack the exact science, the precise frequencies, and yeah, those critical mathematical formulas behind instrument landing systems, primary and secondary surveillance radars, and modern area navigation. If you're prepping for your commercial pilot license exams, this is absolutely the exact toolkit you need to master these complex avionics. So let's get right into it.
Okay, let's dive into this. Here's our quick roadmap for today. First up, Instrument Landing Systems, or ILS. Second, surveillance radars, both primary and secondary. Third, we'll hit radar range and ambiguity calculations. And finally, wrap it all up with modern area navigation, or RNAV.
All right, kicking things off with Section 1, Instrument Landing Systems.
Now, even though satellite tech is everywhere these days, ILS remains the absolute gold standard for precision approach lateral and vertical guidance. It's what gives you that pinpoint alignment during the most critical phase of your flight. Now listen up, because for your exams, you absolutely have to memorize these specific frequency bands. It's a huge pain point for a lot of students. The localizer, which handles your lateral left-to-right guidance, operates in the very high frequency, or VHF band. That's strictly between 108.10 and 111.95 MHz, and it intentionally uses odd tenths to avoid any VOR interference. Then you've got the glide slope for your vertical up and down guidance, sitting in the ultra-high frequency, or UHF band, between 329.15 and 335.00 MHz. But here's the really brilliant part. These VHF and UHF frequencies, they're intentionally paired by AKO. You, the pilot, only ever tune one channel, the localizer's VHF frequency, and the aircraft system automatically tunes the corresponding UHF glide slope channel for you. Pretty neat, right?
So, the crucial point is, how does the aircraft actually know if you're drifting off course? Well, it all comes down to DDM, which stands for Difference in Depth of Modulation. Basically, the localizer transmits two overlapping radio lobes. The left lobe is modulated at 90 Hz, and the right lobe is at 150 Hz. If your aircraft drifts a bit to the left, that 90 Hz signal suddenly becomes stronger, and your cockpit needle commands a turn back to the right to fix it. When those 90 Hz and 150 Hz signals are perfectly balanced, meaning your DDM is exactly 0, congratulations, your aircraft is flawlessly locked onto the center line.
Moving right along to Section 2, Surveillance Radar, specifically looking at PSR and SSR systems.
So once you're actually up in the air, how does air traffic control see you on their screen? How do they know exactly who you are and what altitude you're flying at? The answer is all about the difference between primary surveillance radar, PSR, and secondary surveillance radar, SSR. PSR is, well, it's totally passive. Think of it like shouting into a massive canyon and just waiting for an echo to bounce off the physical metal skin of an aircraft. It tells ATC that something is out there, but it doesn't give them a name or an altitude. SSR, on the other hand, it's highly cooperative. It's an active digital roll call. The ground radar asks a digital question, and the transponder inside your aircraft actively shoots back a digital answer with your specific identity and altitude.
If we trace the path of a typical SSR system, it looks something like this. The ground-based interrogator queries the aircraft on an uplink carrier frequency of exactly 1030 MHz. Your airborne transponder decodes that message, generates the reply, and blasts it back down to the ground station at 1090 MHz. Why two different frequencies? Well, separating the uplink and downlink ensures that the massively powerful ground transmitter doesn't completely drown out the much fainter replies coming from the aircraft. It's a really smart setup.
Okay, let's break down how ATC actually asks for these different types of info. They use different interrogation modes. Mode A asks for your identity, telling your transponder to reply with a 4-digit octal squawk code. Mode C asks for your pressure altitude, which gets reported back in 100-foot increments based on standard atmospheric pressure. And then we have Mode S, which is the modern standard. Mode S completely solves all that legacy airspace congestion because it uses a unique 24-bit ICAO address. So instead of ATC just shouting out to everyone in the sky, Mode S lets them selectively address one specific aircraft out of over 16 million unique combinations.
Now, what's really interesting about this is how it all comes down to microsecond timing. Seriously, your transponder literally tells a Mode A interrogation apart from a Mode C interrogation just by looking at the exact gap between the incoming pulses. The ground station fires off these pulses, which we call P1 and P3. If the gap between P1 and P3 is exactly 8 microseconds, boom, the transponder knows it's a Mode A request for identity.
But if that gap is exactly 21 microseconds, it instantly recognizes a Mode C request for your altitude.
But here's the catch. Radar antennas are not perfect. They actually leak energy out the sides, which creates what we call side lobes. Now, to stop your transponder from replying to these annoying leaking signals and creating a bunch of false ghost targets on the ATC screen, the system uses side lobe suppression, or SLS. Here's how it works. A third pulse, called P2, is transmitted slightly after P1, but it uses a fixed omnidirectional antenna. Because P2 is broadcast equally in all directions, if your aircraft receives a P2 pulse that is stronger than or equal to the directional P1 pulse, your transponder mathematically knows, hey, I'm caught in the side lobe, and it completely suppresses the reply. It's a brilliantly simple solution.
All right, let's shift gears now into Section 3, radar range and range ambiguity.
This is where the physics and math of radar really come into play, a vital area for your exams, by the way. The foundational metric we need to talk about is pulse repetition frequency, or PRF. Basically, this is just the number of radar pulses transmitted per second. But remember, a radar has one fundamental flaw. It cannot transmit and listen at the exact same time. So the PRF dictates the listening time of the radar between pulses. This quiet listening period fundamentally limits how far a pulse can actually travel out to a target and echo back before the radar has to fire off the next pulse.
And this brilliantly illustrates what happens if a target is actually beyond that maximum range. The radar system gets totally confused. If a pulse travels out to a really distant target, it might take so long to bounce back that the radar has already fired its next pulse. So when that late echo finally arrives back at the antenna, the radar wrongly assumes the echo came from the second pulse. This creates a highly ambiguous, much closer ghost target on the controller's screen. We call this phenomenon a second sweep echo.
To prevent this dangerous ambiguity, we have to calculate the maximum unambiguous range, known as Rmax. The formula is quite logical. You take the speed of light, which we denote as c, and you divide it by the PRF multiplied by 2. Why do we multiply the PRF by 2 in the denominator? Simply because a radar is an echo. The electromagnetic wave has to make a full round trip, all the way out to the target and all the way back.
To actually solve this in your exams, you've got to lock in the speed of light constant. That's roughly 300,000 kilometers per second, or about 162,000 nautical miles per second. When you crunch the numbers, the math reveals a vital operational trade-off. A higher PRF gives you much better resolution for tracking fast-moving targets, but it mathematically shrinks your maximum unambiguous range. You can't have both. It's always a trade-off.
Okay, let's leave ground-based radar limitations behind and move into our final segment, Section 4, Area Navigation, covering RNAV and RNP. Under legacy navigation, pilots were forced to fly from one physical ground station, like a VOR or an NDB, directly to the next one. This created these very inefficient, zigzagging airways across the sky. Well, RNAV completely changed the game. It totally decouples your flight path from that physical ground infrastructure. By using onboard computers and GPS, RNAV allows for direct point-to-point routing using virtual phantom stations or waypoints that are defined purely by geographic coordinates. Ultimately, this saves massive amounts of time and fuel.
Let's move to and see how this builds into something even safer: Required Navigation Performance, or RNP. RNP is essentially RNAV, but significantly upgraded. The key difference here is that an RNP system includes internal onboard performance monitoring and alerting, something like RAIM, or Receiver Autonomous Integrity Monitoring. Basically, if the navigation signal degrades or loses its integrity for any reason, the RNP system instantly alerts the flight crew. This guarantees they never unknowingly drift off their intended course.
And because of this continuous real-time self-monitoring, RMP allows aircraft to fly incredibly precise procedures. These are quantified by specific values. An RMP value simply represents the lateral accuracy in nautical miles that the aircraft must achieve 95% of the flight time. For example, RMP2 is typically used for wide en route flying, meaning the aircraft stays within 2 nautical miles of the centerline. But for really tight, curved instrument approaches through, say, mountainous terrain, we rely on a highly precise RMP 0.1, which keeps the aircraft locked within 1/10 of a nautical mile. That's incredible precision.
And there you have it. We have taken a really incredible macro to micro journey today. We've deconstructed the 90 and 50 Hz guidance of the ILS, we unraveled those microsecond pulse timings of SSR transponders, we locked down the exact mathematical formulas for radar ambiguity, and we explored the point-to-point precision of RNAV and RNP. This right here is the core toolkit you need to confidently conquer those DGCA CPL exams.
But, this leaves us with a pretty fascinating, provocative thought to conclude on. With RNP approaches safely achieving 0.1 nautical mile accuracy purely from space and onboard computers, how much longer will global aviation actually rely on the massive, super expensive footprint of legacy ground-based ILS and radar systems? The airspace is evolving fast. Anyway, thank you for learning with this explainer. To ensure you absolutely ace these concepts, make sure you check out clouddeck.ai